So continuing on with section 4.2, we have an example where we're asked to create a growth model. So we're going to be building something that looks like y equals y0 b to the t. So we're being asked to have t correspond to a year where t equals 0 is the year 1990. So in that year 1990, we have an expenditure number of 9.6, and this is in billions of dollars. And then we're also given the information that in the year 2015, the expenditures are $109.2 billion. So let's think about how many years later that is, and t is going to be 25. So we're going to make a model for this data. Y equals, y0 is the beginning amount, 9.6. And then we're going to make a b to the power of t, and we need to figure out what the b is. So that's what we're going to use this other data point for. We're going to say y of 25 equals 9.6 b to the power of 25, and that has to equal 109.2. When you're solving an equation that has an exponential function, the b to the 25th power, you need to isolate the exponential part. So you're going to need to divide both sides by 9.6. So then you're going to have b to the power of 25 is 109.2 over 9.6. Well, to undo to the 25th power, you do the 25th root, or as we also have learned now, you can write it as a fraction exponent of 1 over 25. So you're going to have 109.2 divided by 9.6, and then you're either going to take it to the power of 1 over 25 or the 25th root, and you're going to get b is about 1.102. We'll round it to 3 decimal places. So the model that they're asking me for is y equals the y0 of 9.6 times the 1.102 to the t. So this is the mathematical model. Then we're being asked, according to this model, what were the expenditures in 2014? So let's see, 2014 would be here, and we're being asked what were the expenditures. So that's going to be when t is 24. So we're being asked, what is y of 24? So I'm going to have 9.6 times 1.102 to the power of 24. And I'm going to get about $98.77 billion. And that seems reasonable because it should be somewhere in between these two numbers and closer to the bigger number because 24 is closer to 25. And then we're being asked, if the model stays accurate, estimate the expenditures for 2020. Well, that's going to be in year 30. So we want y of 30. So it's 9.6 times 1.102 to the power of 30, or about $176.90 billion. Wow, that's a lot. Okay, so there's one exponential regression problem in the homework. If you're interested in it, you can look in the Canvas files and see the step-by-step instructions for how to do an exponential regression. But I'm going to skip this for now in the interest of having more time to spend on the calculus. So you can skip that one homework problem and you won't be missing anything that's part of the curriculum. It was just an interesting extra thing that if I have time, I like to add it in. So there's another type of exponential function called a logistic function that we will look at. And then there's also another kind called learning functions that we're not going to address. Logistic functions talk about bounded growth. So they happen when there's some kind of limitation on food or space or money or personnel or what have you. So the exponential part is in the denominator and it has a negative on the exponent. So let's look at an example where we have the percentage of Chinese residents who use the internet is approximated by this function, and this should be a t, sorry, where t equals 0 corresponds to the year 2000. And we're being asked what percentage of Chinese residents used the internet in 2006? Well, that's going to be when t is 6. So we want g of 6. So we're going to have 49.8 over 1 plus 52.8 e to the negative 0.47 times t, which is 6. So let's do that on the calculator. And I'm getting about 12% if I round to the nearest whole number. And it was given that the output of this function is in percent. And so let's go ahead and look at also what happens in 2015. And so that's going to be when t is 15. So we'd have g of 15 equals 49.8 over 1 plus 52.8 e to the negative 0.47 times 15 now. And I'm getting about 47.6%. So this model is predicting a lot of growth between 2006 and 2015, and it would be interesting to check and see how close it is to actual. Okay, so that's the end of 4.1 and 4.2. And now we're going to get into section 11.8, where we're actually working on the derivatives of these functions. So this is probably going to be your new favorite derivative because the derivative of e to the x, it's e to the x. It's the only function that is its own derivative. But then we also have to take into account, what if it's e to the power of some function of x? Well, then the chain rule tells us it's e to that function of x, don't change that function, times the derivative of the function. So if the exponent is anything but plain vanilla x, you need to times the derivative of the exponent in the front. So let's look at example A here, and we're going to have y equals, and you're going to have the derivative of the negative 4x times e to the negative 4x. This is going to be y prime. So the derivative of negative 4x is negative 4, and then e to the negative 4x. So that's your answer. So then g prime of x, example B, is going to be 6 times the derivative of x over 2 times e to the x over 2. Well, the derivative of x over 2, remember that x over 2 can be written as 1/2 x. So it's going to be 6 times 1/2 e to the x over 2, also known as 3 e to the x over 2. Okay, and then C, we're going to have that y prime equals the derivative of the 4 minus x cubed times e to the 4 minus x cubed. And we know the derivative of 4 minus x cubed is negative 3x squared, and then e to the 4 minus x cubed. And the last one, y prime equals 4 times the derivative of 2x squared minus 4, e to the 2x squared minus 4. So that's going to be 4 times 4x, e to the 2x squared minus 4, which is 16x, e to the 2x squared minus 4. Okay, then we need to be able to combine this with other rules. So this first example is a product rule. I have the product of a polynomial and an exponential function. So my u function is the 6x squared minus 5x, and my v function is the e to the minus 3x. So then my u prime is going to be 12x minus 5, and my v prime is going to be negative 3 e to the negative 3x. And then I'm going to do my multiply to get my product rule, and I'm going to have 12x minus 5 times e to the minus 3x plus 6x squared minus 5x times negative 3 e to the negative 3x, and that's y prime. Well, you need to recognize that this is two terms that each have an e to the negative 3x as a factor. So we need to factor out e to the negative 3x. And in the first term, I have left 12x minus 5 plus, in the second term, I have 6x squared minus 5x times negative 3. So then I need to simplify what's inside the parentheses here, and I'm going to have 12x minus 5 minus 18x squared plus 15x. So my final answer is e to the negative 3x times negative 18x squared plus 27x minus 5. So that's a good place to pause, and then I'll make more movies for the logarithmic part.